Hi there. Thought we'd revisit the friction on an inclined plane. Some of the questions from 18C now. So in a previous result, we said we looked at the situation if these are the only three forces acting, and we looked at a specific case if there is limiting equilibrium, the beautiful relationship there is between theta and mu. In this case, we want to look at the questions deciding if there is acceleration, and if so, how much there is. So if there is acceleration, it's definitively down the plane. Therefore, if the acceleration is down the plane, perpendicular to the plane in that direction, so perpendicular to the plane, there must be equilibrium. So in this direction, we have the forces balancing. Now, because the maximum friction can be as mu r, we get the maximum friction could be as mu mg cos theta, mu times that value of r. To decide whether there is acceleration, we need to compare mg sine theta, which is the component of the weight parallel to the plane, with the frictional force. If we find that the mg sine theta is less than the maximum frictional force, we're going to get equilibrium. And in that case, friction balances mg sine theta. Okay, friction doesn't take its maximum value unless mg sine theta is the maximum that friction will be. So friction only balances mg sine theta. Right, if friction is less than mg sine theta, there isn't acceleration, there isn't equilibrium, so it is accelerating, and we can apply Newton's second law. Now, the most important diagram on this slide is this one here, how we get the components of the weight parallel and perpendicular to the plane. Okay, 18C, I picked a couple of ones from question 1. So if you want to read them, I've picked 1B1 and I've picked 1C2. So you may want to familiarise yourself with those questions. In this top corner, I've put the little diagram to explain how I'm getting the components of the weight. So I've got weight here, and I've got the components perpendicular to the plane, which will balance the normal reaction if they're the only three forces, and the component parallel to the plane, which will oppose friction in a lot of cases. Okay then, so 1B1, the angle is 30, mu is 0.8, and the mass is 1 kilogram. So we've just got G here. So parallel to the plane we have equilibrium, which means the normal reaction is 8.49, which means the maximum that friction can be is 6.79. Parallel to the plane, the component of weight is G sine 30. And we can look at that diagram again to decide that. G sine 30 is 4.9. 4.9, the component of weight, the component which would be trying to take the object down the plane, that's smaller than the maximum that friction can be. So the particle doesn't move, it's in equilibrium, and friction is only 4.9 to oppose the component of weight. So the maximum that friction could be is 6.79, but in this case it's 4.9 because the component of weight it's opposing is 4.9. In 1C2 we have a greater angle, a smaller value of mu, so a slippier slope, and it's a different mass. Bit of a red herring that, the mass won't make a difference. So parallel to the plane we have equilibrium. The normal reaction is 34.6 because it balances a component of the weight. Therefore, the maximum friction can be is 3.46. Parallel to the plane, the component of weight is 34.6. Now that is 10 times the size of the frictional force, isn't it? So because it's much bigger than there's no equilibrium, so the acceleration would be 6.2, but we're not actually asked for that. We're asked for the size of the frictional force, aren't we? Which is 3.46. Right, now, an absolutely brilliant one. So try the others between question 1 and question 11. If you're not sure about them, you can email us at school and we'll see if we can put an answer up. But 18C is brilliant. 18C, question 11, is a fantastic question. So read it now. Read the one about the toy hovercraft with the mass of 0.5 kilogram placed on the inclined plane. Read it and understand what the situation is. So, in part A, the fans are horizontal. So we have a horizontal force of 10, and then we have these other three forces, 1, 2, 3. Now, perpendicular to slope, we still have equilibrium, but perpendicular to the slope, there are now three forces which have an effect. There's normal reaction, a component of the weight, and a component of the force of 10, the driving force. Why is it sine 30? You've got to convince yourself that this angle in here between the plane and the 10 is the 30 degrees. Okay? I think it's obvious. I think it's because it's corresponding to the angle of 30 there. Convince yourself by drawing a bigger diagram. So the normal reaction turns out to be 9.24. The maximum of friction could be is 0.924. Now in the question it implies there's acceleration. So in the question it says what's the acceleration? It's implied. I think we're safe to jump straight to Newton's second law without checking if the driving force up the plane, the 10 cos 30, is big enough. It's implied, it says it's accelerating, so Newton 2 parallel to the slope. So we've got the driving force up the plane, 10 cos 30, opposed by two forces, the frictional force, and because we're told it's accelerating, I'm assuming that it's the maximum it will take, it can be, and then a component of the weight. And that's equal to, that resultant force is equal to half A. The mass, half, multiplied by A. Left-hand side becomes 5.29. If you double that, you get 10.6. 2 sig fig must be what's appropriate this time, looking at the values in the question. Right, part B. The fans are parallel to the slope. Okay? Parallel to the slope. So driving it, and again, the question says the acceleration up the slope. So I think we can assume that, we can infer from that, that the 10 is up the slope. So parallel to the slope, sorry, perpendicular to the slope, we have equilibrium. Now in this case, we only have two forces with any effect perpendicular to the slope. We have R and that component of the weight again, giving a normal reaction of 4.24, a maximum of friction of 0.424, and because the question says it's accelerating, we can safely assume that that's the value friction takes. Okay? If it's accelerating, friction takes its maximum value. So, parallel to the slope, it's Newton's second law, and I should have said Newton's second law here. it should say Newton 2 parallel to the slope. So the driving force up the slope opposed by those two forces down the slope, okay, in that direction. Got to use the components. That's all. This whole chapter has been about components of forces. The chapter we do on the projectile is about the components of the velocity. And work that through, you get A is 14. Now, if the fans are at an unknown angle, can we find what angle maximizes the acceleration? So first of all, a diagram with 10 at an angle of theta to the slope. Okay, it's accelerating up the slope. So in the direction it's accelerating, we do Newton's second law. In the other direction, we balance the forces. And this time, it's R, a component of 10. Now remember, this is the crucial thing, that direction. And that is opposed by half G, and there should be a trig operator there. But you'll see why I'm not so worried. I'm going to rescue that in a second. Parallel to the slope, we get this. Very similar to the expression we had in part A, but we have this time a component of the 10. Now, this component, these two components, one should be sine, one should be cosine, could work in perpendicular directions, and that matches. Maximize A. We've got, the only thing we can change is the theta. The only thing we've done before with the idea about maximum minimum has been some sort of differential. Right, already I'm thinking this is more complicated, not enough space. Let's do this properly. So, first thing I've done is a proper size diagram. Don't be scared on the exam, or whatever you end up doing. Proper diagram, if need be, redraw it. Perpendicular to the slope, we have R, a component of the 10, and a component of the weight. And that's what I meant by I'd rescue it, because I already knew I had this one drawn. Right, and that gives R in terms of theta, and it gives friction in terms of theta. Parallel to the slope, we're going to do Newton's second law, because that's the direction of the acceleration. Okay, accelerating, Newton 2 in the direction of acceleration, perpendicular that we have equilibrium. So we have 10 cos theta. Oh, I realise, make that the 10 cos theta, and the other component should have been that one there. Sorry. Take the friction. And also the component of the weight this time is going to be in that direction. The 4.9 sine 30, that's equal to half A. What do we get? We get this. If I substitute friction in there, we get, I'm just going to use a slightly paler colour now so we can see everything underneath it. So we get 10 cos theta, take 2.69 as half A. We get A is 20 cos theta, take 5.38. Right, if we're looking to maximize something when something else is changing, it's about differentiation. It's an old year 12 method, it's optimization. A is maximized when dA d theta is 0. We couldn't do this in year 12 because we need to be able to differentiate trig functions. dA d theta is minus 20 sine theta plus 2 cos theta. At a maximum, we know that, and I'm just going to make life easier for ourselves so we can read that. Let's read those again. At a maximum, dA d theta is 0. So if if this bit here, if the AD theta is 0, that right hand side, this bit here is 0. Those two things must be equal. Tan theta is a tenth is 5.7. Is it a max? Only if the second differential is negative. If we differentiate the second time, we get that. We're going to put an acute value in. 5.7 is an acute value. Both cos theta and sine theta are positive when theta is acute. So if we've got minus 20 times one and minus 2 times the other, that's definitely negative, which means it's a maximum. And that's a brilliant question. Try the other questions in 18C, try the questions in the mixed exercise. Email us if there's one you want us to particularly go through, or submit your work for it. Brilliant.